We are glad to have to start the second semester of the stability versus testability. We mentioned already in the first semester, mainly in the talk of Jonathan Musayev, that there are some connection with computer science, and today we will get one of the world experts, Irit Dinur, if not the world expert, Irit Dinur, from Weizmann Institute, who will talk about stability and testability in computer science, the PCP theorem, etc., etc. The stage is yours, Irit. Thank you very much.
Thank you very much for the invitation, and thanks people for coming. It's not easy to be listening to Zoom seminars, so I appreciate you being here. And so unfortunately, I haven't followed the seminar as closely as I had planned. Maybe this semester will be better, but so I wasn't able to kind of tune my talk based on the talks that you guys have heard. So please ask questions and kind of direct me. The talk is a little bit flexible. The first part is PowerPoint, but then I'm going to move to the iPad, so I can be quite flexible in what we choose to talk about. Okay, so Alex asked me to talk about general things. I wasn't sure exactly what, so I'm going to start by a kind of survey-ish description of how I view testability questions in computer science, and maybe hopefully related to stability as per this seminar. Okay, so the most relevant sub-area of computer science is called property testing. It's a field that is concerned with algorithms that are quick and dirty. They don't even have time to look at their entire input. They look at just a little part of the input, and based on that, they make their decision. So a priori, it looks very strange, maybe. But the point is that you look at a random part of the input. So there is no one part of the input that you focus on. The algorithm makes some random choices, and based on those, decide where to look. So in expectation, it does look at the entire input. And why would we even bother caring about such weird algorithms that only look at a tiny part of the input? Well, actually, in modern times, motivation is very clear. Sometimes the input is just huge. You don't have time. You cannot afford to read the entire input, whatever it is. If it's the internet, if it's just looking at the world and trying to deduce things about the world, you're going to do it based on your local little picture. And we want to understand from a theoretical point of view, in what situations you're allowed to deduce global deductions based on local point of view. Okay, sometimes your input is not even laid out to you. It's not some huge graph that is there, but you don't have time to look at. It's not even given to you. For example, maybe you get a computer program, and this program describes a bunch of input-output behavior, but you don't have the entire truth table of the computer program written for you. So it's given to you implicitly. Nevertheless, you want to understand some structural behaviors of this implicit input, like this computer program, and you can do it by feeding random inputs and seeing what outputs you get and making some decision based on that. Another reason for wanting to run a property testing algorithm is as a preliminary step. So suppose you are able to read the entire input and to do this heavy calculation or computation, but it's expensive. So maybe you first want to run a much faster rough algorithm, a property testing algorithm that will only look at a little part and make some approximate decision. And if the test gives you the green light, then you will devote a much more heavy computation and read the entire input. So what would be an example for such a behavior? For example, suppose you have some error correcting code and you're trying to, you get some string and maybe there is some noise in the string. You need to decode the string. To decode the string means to clean it from the errors. So we have algorithms for that, but these algorithms need to, of course, read the entire string and do some computation. and they will only work if the amount of noise is small. So they will not work if there was too much noise. So what you can do is run a property testing algorithm to check how much noise there was. Turns out there are such things. And if the check succeeded, then you can go ahead and do the decoding. Okay, so these are just a number of different motivations for being interested in this, but you can also feel that it's a very basic question. You want to deduce something global from looking at a very small part of the picture, what we call a local view. Maybe I should also comment that when you think about it, maybe you have in mind things like calculating the average of a number of points. This is a natural thing you can calculate without reading all of the data. You can just sample and read and do some local average. However, in property testing, we're thinking of things beyond such statistics. We're thinking of things that are more subtle, as you will see. Okay, so let me give you a couple of examples of canonical property testing questions. The first one is not so canonical, but I think it's one that I learned from this seminar. So I want to just tie it together to questions that you guys have probably heard about. So this is this question. You get two permutations over n elements, and you want to know if they commute. So of course you can go through all the possibilities and see if they commute. But more property testing like thing would be to just select a random element from 1 to n, some index I, and to run t on I and then s on t of I, and to do it the other way around, s on I and then t of s of I, and to see if you got to the same place, right? And the papers in this line of work of stability actually show that if this test succeeds, so if actually this reading these 4 points led you to conclude that actually it's possible that these two things commute, and if this happens with high probability, then S and T, maybe they are not actually commuting permutations, but they must be close to two permutations that are commuting. So you can change S a little bit and change T a little bit so that they actually do commute. And let me say that this is actually, this issue of changing is really inherent, because the way this is set up, you're only going to read a tiny part of the input. In our case, a tiny part of these permutations. So if someone goes and changes the value of the permutation in one specific location, the probability that you will even notice this is negligible. Okay, it's like 1 over n. So you cannot be expected to know for sure whether S and T commute. The best thing you can be expected is to know if they're close to commuting. So you must allow this approximation, this ability to change S and T back to perfectly commuting permutations. Okay, but this example, of course, is not only true in the setup of permutations. So let me move to talk about questions that are more mainstream in property testing. So here is one. You have two groups, and you are given a mapping between the first group and the second group, just a function. And you want to know whether this function, so sorry, this capital F should have been a little f, sorry. You want to know whether this mapping is a homomorphism, okay, from G to H. Of course, you're not going to read the entire truth table of this mapping. What you want to do in a property testing setup is to just probe it in a few locations. So you're going to read it at location X, you're going to calculate f of X, then you're going to calculate f of Y, and then you're going to calculate f of X times Y. And you're going to accept, the tester will say, okay, this looks like a homomorphism if f of X times f of Y equals f of XY. So you're reading your function here on only 3 points, and we will see later that this is actually a good tester. It's not a priori clear. So the homomorphism thing is an example of what sometimes people call algebraic property testing, dealing with objects that have some algebraic symmetries and so on. And a very large field is the more combinatorial property testing, mostly dealing with graphs. So here is an example. The input object here is a graph. You think of it as being given by an adjacency matrix. And the tester is not going to read the entire graph. It's going to read just a couple of edges maybe. And some questions you can try to understand is, does this graph have some graph properties? So examples of graph properties that were the first ones to be studied are, is this graph bipartite? How can you check without reading the entire graph if it's bipartite? Another question is this graph triangle free? Okay. So these are some examples. So let me make a question.
You are going to tell us what the answer to these last two questions?
Yes. You don't know them yet? Yeah, I'll tell you. I'm going to go into them in a bit more detail soon. So, but let me make a few comments about just the nature of this whole study. Okay, so as we said, the decisions of the algorithm, the property testing algorithm, first of all, the algorithm must be randomized. It can't be that if you have an n by n matrix for a graph, the algorithm will always only look at the first few rows and columns. That's absurd. So of course, the algorithm needs to be randomized. The second thing is, like we talked about with the permutations, the output of the algorithm should have some approximate nature to it. You can't expect the outcome to be, yes, the graph is exactly bipartite. For the same reason as we talked about with the permutations. Someone can always change one edge, introduce a triangle in this graph, making it not bipartite. The chance the algorithm will notice it is negligible. So you must allow approximation. A second kind of property of this field, the hallmark of property testing, is that the property testing algorithms are almost trivial. Usually they're like, you know, look at a tiny part of the object and check whatever you can possibly check on this local view. Say yes if the checks passed, say no if the checks didn't pass. So the algorithm will be trivial and boring. But the analysis is not so trivial and boring. Sometimes it's really surprising and interesting. And in some sense, this is the beauty of this area, that the fact that the algorithm is trivial means that it's very easy to implement. So it's a very desirable property for an algorithm. And the fact that the analysis is non-trivial, okay, maybe it makes you, to me, it's more interesting. Okay, so what are the main directions that people study? This is algebraic property testing. This is actually where the field kind of emanated from. So we have these homomorphism testing, which is a generalization of something called linearity testing. There's low degree testing. I'll talk about these soon. And these came really from the study of probabilistically checkable proofs and trying to construct a certain kind of encodings that are stable encoding. So we will later discuss what it means to be a stable system of equations or stable encoding. So this is algebraic property testing, and there's also graph property testing. It was introduced, I think, in '98 by Goldreich, Goldwasser, and Ron. And this talks about the graph properties, another combinatorial type of property testing. And there's many other areas of property testing these days. I don't follow it enough, but you can talk about distribution testing, where there's some distribution, you sample from it, and you want to understand some structural properties of the distribution. For example, is it unimodal? Okay, I don't even know what kind of interesting questions people ask there. And this is also related to other areas that are very important, such as learning. You have a lot of data and you want to learn some structure. It's related, but it's not the same. There's streaming algorithms where you only look maybe at the input one time. You have to remember what you can, and you have a bounded amount of memory. So many different models in which the input is much bigger than the resources of the algorithm. Okay, so I won't focus about any of those things. Let me talk a little bit more about property testing. And in particular, I'll start with property testing for graphs. Okay, and the two questions that Alex asked about. So the first one will be bipartiteness. So this is an example of property testing. We are given a graph. As I said, we are given it by the adjacency matrix. And we want to know whether or not this is an adjacency matrix of a bipartite graph. However, we're not going to read the entire matrix. instead, what we're going to do is choose a bunch of vertices. We have some epsilon parameter, it's a distance parameter, we'll soon discuss it. And what we're going to do is just read the entire subgraph induced on these k vertices. So all possible k-squared pairs, we're going to see if the edge is present or not present. And if the graph we got, which is a constant size thing, is bipartite, the tester will accept. If not, it will reject. So you see it's a randomized algorithm, right? Because the choice of the k vertices is random. Okay, so now I need to analyze this tester. How well does it function? So clearly, if the graph is bipartite, the tester will always succeed. Okay, so there is a global bipartition of the vertices into white and black. And no matter how you select the subset of the vertices, you can restrict this bipartition and the tester will accept.
But what happens if you choose on one side?
Sorry?
What happens if you choose only points on one side?
Okay, good question. So if the tester chooses only points on one side, it will ask the adjacency matrix about all the edges between these points. It will see 0 edges, right? No edges. Okay, so it's bipartite. Okay, so the interesting question here is what happens if your graph is not bipartite? And notice here that the epsilon suddenly appears, because I'm not interested in what happens when the graph is not bipartite, if it only has one edge preventing it from bipartite. The interesting situation is when the graph is really far. What does it mean really far, or epsilon far? It means you need to change epsilon times n squared edges to make it bipartite. This kind of graph is a graph that I expect the tester should reject. Okay, if the graph, you need to change fewer than epsilon fraction of the edges to make it bipartite, for this kind of algorithm, you count it as if it's bipartite. Okay, so suppose this is our graph. What happens? Okay, so I'm not going to show the analysis here, but GGR and later Alon and Krivelevich improved the parameters showed that indeed the tester will reject with the probability, say 2/3. And there's an interesting question here. How many vertices do you need to probe in order to get this probability 2/3? Okay, and I think GGR proved 1/epsilon squared, and Alon Krivelevich showed that it's almost 1/epsilon. So, okay, so far, what do we take from this? If you have a graph that on local pieces, it looks bipartite, then the theorem of GGR and Alon Krivelevich is that it must be globally bipartite. So this property is testable. So notice that we are relating two different measures. One measure is the probability over local pieces that this local piece is bipartite. That's a number between 0 and 1. And the other measure is how many edges do I need to remove from the graph in order to make it bipartite. It's two different measures. And what such a theorem is telling us is that these measures can be related to each other. Okay, let's move to triangle freeness. Okay, so it's clear what the triangle free graph is, right? Okay, a graph can be very dense and yet not have any triangles. For example, a bipartite graph is such a graph. So what would be a natural way to test if a given graph is triangle free? Well, here is one idea. Choose a triple of vertices and see if that is a triangle. If it is, you can choose another random triple, check if that is a triangle, and repeat it k times. Okay, so this is our test. Okay, so clearly, again, if your graph is triangle free, no triangle will be found. All of these tests will succeed. Probability 1.
Irit?
Yeah.
Sorry that I'm stopping you. I wanted to ask something about the previous thing. Actually, like this becomes interesting only for graphs with O of n squared edges, right?
Excellent point.
So for
Yeah.
example, for D regular graphs, for some D fixed, this is just like you can always make it bipartite by just deleting all edges or something.
That's a
In
great
this
point.
sense of the
This is called the dense model because we're for free allowing epsilon times n squared edges to change. So any sparse graph is the same as the empty graph in this model. So indeed, this is only a very small sub area of property testing. There's been a lot of work trying to import the results that are quite natural in the dense model to sparse situations. It's much more difficult. So I'm only focusing now on the so-called dense model. But that's an excellent point.
yeah, thanks. So you say that for D regular graphs for some fixed D, this is like, okay, maybe I'll ask at the end if you have any references for this case.
Sure. Yeah. So for example, I said that the graph is given by the adjacency matrix, but in the sparse model, a better model is to get the graph by the, forgot what it's called, the linked list model or something where for every vertex, you just have a list of all of its neighbors. I don't remember the name of the model, but sure, I'll be happy to give you some references later. Okay, but let me focus on the dense model. So of course, if the graph is triangle free, checking a bunch of triangles will be fine. Now I want a theorem that says if the graph is epsilon far from triangle free, then the tester rejects, sorry, it should be either, it should be that it rejects the probability above 2/3. Apologies. Okay, you want to be able to notice the fact that it's far from triangle free. So what does it mean, epsilon far from triangle free? It means in order to kill all the triangles, you need to remove at least epsilon times n squared edges. If you remove fewer than that, there will remain a triangle. Such are graphs that we expect to detect in our testing. So now comes the question, what do you think K should be? The number of triples that this tester should read before we can prove that such a theorem is correct. So let me just explain again the question. My tester is going to choose a bunch of triples and check whether they're triangles. And I'm going to hope to prove that if none of these were triangles, then the graph must be close to triangle free. There cannot be more than epsilon n squared edges that I need to remove to kill all of the triangles. Now, a priori, it could be that this is not a property testable property. Triangle freeness, it might be that the number of triples you need to choose doesn't only depend on epsilon. Maybe it depends on the number of vertices in the graph. Right, so the answer is yes, it does depend only on epsilon and not on the number of vertices in the graph. However, what is K as a function of 1 over epsilon? Previously, we saw for the bipartiteness, K was 1 over epsilon or 1 over epsilon squared. So I think it's natural for a triangle to expect this to be maybe 1 over epsilon cubed or some polynomial in 1 over epsilon, right? But maybe it's bigger, maybe it's exponential, maybe even bigger than that. So it turns out that the first paper to prove that triangle freeness is testable showed that you can take K to be a tower function of 1 over epsilon. You know what the tower function is? It's 2 to the power of 2 to the power of 2, 1 over epsilon times. Maybe it's even 1 over polyepsilon, but never mind. So they proved this huge function of epsilon. It's not a function of the number of vertices. And if you read this many triples, you'll be fine. This statement about the tester rejecting with high probability is going to work. By the way, does anyone know where this tower comes from? In this proof? So the way to prove these things is by using the semi-ready regularity lemma, where you take any dense graph and you can always partition it into parts. This is the regularity lemma. And then you can use these parts to count how many triangles. If you throw randomly enough triples on your graph, these triples will kind of go between all possible parts, if the number of triples is large enough with respect to the number of parts. And in the regularity lemma, the number of parts is a tower function. So in fact, Noga showed that some counterexample related to the regularity lemma implies that you cannot do with just polynomial in 1 over epsilon. So they showed that a tower is enough. Polynomial is absolutely not enough. But where is it in the middle? It's an open question. So I mean, I find it quite amazing because the question seems so simple, so it's combinatorial, you subsample, it should work, you just do the calculation. But no, something more, more complicated and interesting is going on here.
Isn't there an improvement to a tower of depth like log 1 over epsilon?
By now we know better. Yes, by now we know much better, but we still don't know anything from 1 over epsilon raised to the power log 1 over epsilon all the way up to this tower that you mentioned. Okay.
Irit,
Yeah, please.
do we know that there is no, like they answered only this about this specific tester, right? Like maybe there is a better potentially tester for triangle freeness?
Yeah,
or can we, or maybe Alon's work says that any tester will need more than like.
Yeah, I don't think it matters. There's a lot of work on different variants of property testing. The most interesting one is called adaptive versus non-adaptive. So if you're going to read, say, k vertices, you might as well read all the k choose 2 edges between them. So the only thing that can be different up to this k versus k choose 2 is whether by reading something, you're going to change which other vertices you're going to read. For example, if you want to follow a path or something like that. And this is what we call an adaptive tester. So I'm not familiar with the literature, there's so much work on these things. So a lot of this terrain is mapped out and there's separation, some things you can or cannot do. There's an excellent book by Oded Goldreich giving an introduction to property testing. And if you're interested in these things, take a look there. Okay, so now let me talk a little bit about algebraic property testing. So here is an example. You fix some finite field f, and you look at a function from f to the m to f. It's given to you by the pointwise evaluation. It's just a truth table. And the question is this truth table, does it correspond to a low degree function? Is there a low degree polynomial whose evaluation agrees with these values? Okay, this is called low degree testing. It's a very famous property testing question. It was one of the initial questions that is very important in the construction of PCPs. So people studied that and proved the theorems about low degree testing, and this is kind of the beginning of this entire area. Another question that's, you can view it as a special case, is if the finite field happens to be just a field of 2 elements and the low degree happens to be degree 1, then what we have is just given a function, is it linear? Okay, can you write it as a linear function? And this is also very one of the first property testing results and a very famous result. And it's somehow much more interesting that it may, if you haven't seen it, it may look trivial to you, but let me talk about it a little bit. So what would be a natural test for whether a given function, so basically, what does it mean you have a truth table? You have 2 to the n values, and you want to know whether these values correspond to a linear function or not. And you're not going to read the entire thing, right? We're in property testing situation. You're going to only read a few bits. So what would be a nice tester to do? Okay, choose 2 random points, x and y, and then you read your function in 3 points, f at point x plus y, and in the 2 points that you chose. And check if this equation holds, f of x plus f of y equals f of x plus y. So clearly, again, if f is a linear function, we'll succeed with probability 1. Every linear function satisfies this. The more interesting thing is to say, well, what happens if f is not a linear function? So again, like in the case of graphs and permutations, we never care about f being a linear function where one bit was changed. That's not interesting. The interesting situation is whether f is epsilon far from any linear function. So the closest linear function is still epsilon times 2 to the n bits far from your function. Okay, so suppose f is such a function. Then I want to say that the tester will say yes, so the fraction of triples x, y, x plus y for which f succeeds is no more than 1 minus epsilon. Okay, this is a theorem proved by Blam, Luby, and Rubinfeld. And if you're not happy with this probability 1 minus epsilon, remember that you can just repeat the test with a bunch of triples, not just one. So you can.
Irit, I have some vague memory that there was a constant of 2/9 somewhere.
Ah, you're saying between this epsilon and this epsilon. Yes,
Yeah.
you got me. I kind of don't care about constants here, but the 2/9 is appearing in the next slide. So let's see. Sorry?
Irit, can you maybe say, like, so this is like a specific example of the group homomorphism. So can you say, so what is, except for it being very practical example, what's the difference, say, in the proof or anything like that? Is it much better than the standard testing for group homomorphism?
No, it's the same. I'll revisit this in maybe a slide or two. I don't remember. So then you can ask again.
Irit, you know why I remember this 2/9? Because this 2/9 appears also in the work of Gromov on topological and geometric overlapping, and suddenly in this, you know, exactly the same number appearing. I don't see any connection, maybe completely accidental, but I'm curious about that. And the two areas are somewhat related. They're not
interesting.
totally
And I never knew about this 2/9, so that's interesting actually to talk about it later. Okay, but let me continue to this slide. Okay, so okay, just going back. So what we have here is, on one hand, I have two distances. One distance is just the distance of my function from a linear function. What fraction of inputs I need to change to get to the closest linear function. That's one distance. The other distance that I have is on my function f, what fraction of triples cause the test to reject. The fraction of rejecting tests, or the fraction of accepting tests, okay? And now I have a graph relating the two things, okay? So on the x-axis, we just have the distance. It's the distance of my function from a linear function. And on the y-axis, I have the rejection probability. Okay, I guess I don't see here 2/9, but I'm sure, wait, do I have another slide? No, another slide, no. Okay, so I'm sorry, I don't have the 2/9 over here, but I want to point out something very interesting, which is this function in red is tight, meaning that there is both the analysis and counterexample showing that the relationship between distance and rejection probability is not even monotone. Okay, you see when the distance cannot be bigger than half, right? Because the linear, every function is half close to a linear function. But the distance, or an affine function, but you see here that when the distance is close to is quarter, the rejection probability is maximized. But then when the distance grows, the rejection probability goes down. So this is far from you know, a complete picture, and I don't think people were super motivated to understand this more. But it's just clearly something strange is going on here, and despite looking like a very innocent question, it's not. Okay. Okay, so now I want to move to this homomorphism testing, which is really a generalization of the linearity testing. How is it a generalization? When G is the group 0, 1 to the n, and H is the group 0, 1, then being linear is exactly being a homomorphism between these two groups. And we have the same test analyzed by Ben-Or, Coppersmith, Luby, and Rubenfeld. I don't know if I have anything here. I guess I wanted to show something about the proof. So let me now share my board. Yes. Okay, so I guess, okay, I'm going to say something about the proof of these two theorems, the BLR theorem and the one with Ben-Or, Coppersmith, and Rubenfeld. I guess it's a different B, Coppersmith, Luby, and Rubenfeld. This is the homomorphism testing. Both proofs are roughly the same. Okay, so it would be somewhat easier for me to describe the proof in the case of the linearity testing. But I think you capture all of the ideas. So I'm not going to tell the entire proof, but I do want to give you a sense of what kind of arguments go into this kind of proof. Okay, so what is the theorem? The theorem is this. I have a function f it's given to me as a truth table. So I have 2 to the n different values. And I know that the tester succeeds with probability 1 minus epsilon. Meaning for a random triple x, y, x plus y, usually the function satisfies this equation that is written here. Okay, so I know that this is usually satisfied. And what is my goal? My goal is to find a linear function. So f hat is a different function that is absolutely linear. So what it means is that you can write f hat in the variables x1 to xn is just summation ai xi mod 2. So f hat is an honestly linear function. You can find a linear function f hat such that the distance between f and f hat is epsilon. Distance meaning the fraction of points in 0, 1 to the n that they are different. Okay, so how do I change it? So the first step will be to define f hat. Okay, I don't know f hat, right? So I'm only given f. But I'm going to define f hat using the popular vote. I'm just going to look at all, for a given x, at a given point x, I'm just going to look at the popular vote of the value f of y plus x minus, so since we are over f2, I can write plus, it doesn't matter, minus f of 1. Okay. Clearly, if f was a linear function, this value should have been f of x, right? And also, if xy, x plus y were one of the good triples, then the value I give f hat is equal to the value of f of x. Okay, but for some y's, maybe you get one value, for other y's, maybe you get another value. We're going to take the popular vote. So we have defined our function f hat. Okay, and now I view this as a decoding step where from f, which was maybe a noisy object, we extracted a function that we will now prove is a perfectly linear function. Okay, so the next step will be to prove that this function that we extracted is not too far from the original function. It's close to f. And this is actually easy. The reason is, as I said, for triples, for situations where x, y, x plus y satisfied the test, this value is equal to the value f of x. And if this happens often, then this value is also equal to f hat of x. So both of them are equal. So it's actually a very easy argument to show that this f hat is close to f. That's not a big deal. The more interesting part, I'm not going to do it, I just want to give you a flavor of how the proof should go, is to prove that this object that we define through this popular vote is a linear function. And what you prove is that f hat satisfies this equation, f hat at point A and point B and point A plus B, their sum is always 0. And you're going to prove it for every pair A and B, not just for most pairs. So whereas for f, we only had this equation hold 99% of the time, for f hat, it holds always. And the way you do it is by, you take the point A, and so you take the point A and you somehow move to some other points, A prime and A prime plus A. So This is a triple where the test holds. And you do the same for B. And you do the same for A plus B. Sorry, B. And somehow you use some algebraic cancellation to show that if for many A primes, the triple A prime is a good triple, it means that the F hat satisfies this equation. So not going to go into the details now, but that's how the proof looks. Now let's see if I can share again. Yes. Okay. So this was algebraic property testing. And I told you that in the first stages of this area, property testing, the algebraic questions were the most popular question.
Yeah, I have a small question about this proof and maybe the relation to the homomorphism. So it seems that the way to go to the actual linear function. So if you have a pair where the F hat doesn't A and B and A plus B, where the F hat doesn't has what you want, then there's too many neighbors, neighboring such bad Y's that would damage the popular vote of the definition of F hat.
Right.
Which kind of saying that the graph, because the graph here is a cube, so kind of something about the connectivity of the graph or the degree of the graph, which reflects on the structure of the group. So does that somehow get into the point where you're looking at the homomorphisms on the homomorphism setting, where you have like some restriction on some restriction of the local structure of the group that can tell you whether it's testable or not, something of this form?
No, actually, the homomorphism testing works for every group, every non-abelian, abelian, doesn't matter, every finite group, it works. And the thing is, the graph, okay, it's not clear what the graph is, but notice that really it's like the Cayley graph with all generators, so it's a complete graph. Because you move from G,
Yeah.
and then you move from other G. So, yeah,
Okay.
it's not clear what graph there is. The graph does play a role in what some people have studied called the de-randomized homomorphism testing, where you want to make fewer, you want to use fewer random bits. So you don't want to choose both X and Y at random. Maybe you choose X at random, and then Y maybe in a de-randomized way. And maybe you use an expander for that. And there's a very nice paper by Wigdersen and Spielka showing that for certain, I think for any Cayley graph that's an expander, this will work. Cayley graph of this group, of the group.
Cool.
Okay.
Thank you. Sorry.
More questions?
Irit, so how do they use the expansion? Like, how do they choose the two elements? They just go a few steps in the expander? This is the point? Like,
The test, so suppose you have a Cayley expander, okay? So the test will choose a random point in the random generator. So you have G times S, and S. Maybe you need to shift everything so that you don't always query S. I don't remember. Maybe you need to choose like G times S, G times S prime. Okay, I don't remember. But interesting, this is how to do the test. When you do the analysis, you define like we did. Remember, we defined F hat by the popular vote over a bunch of things. They define the popular vote even over triples that are not part of their test. I find that interesting. But yeah, anyway.
You repeat again the last sentence. You define the popular vote over what?
All triples, even ones that don't participate in your test. you have your function defined on every element of the group G. You tested only triples that come from some Cayley graph. But when you do the popular vote, you can look at all possible triples, not only the Cayley triples. Okay.
Because
So,
you don't really do it. It's just kind of a mental question.
right,
So
only in the analysis, right? So you're allowed. Yeah. Okay. So I wanted to. The last part of the talk will be about locally testable code. So the reason people got into these algebraic questions of low degree testing, linearity testing, was because they were trying to construct in various ways encodings that kind of in retrospect, you can think of them as what we call locally testable code. So what is a locally testable code? It's an error correcting code. So I assume people know what this is. It's a think of it as a linear subspace where all the vectors are have high weight. They don't have sparse vectors in this linear subspace. And the reason this is a very useful object is because you can encode your messages this way. And two messages are two elements in this subspace. They must be very far from each other because their difference is also in this subspace. So it must have many, many ones. So this is very useful for communication. It's a very basic object, error correcting codes. And what is a locally testable error correcting code? It's an error correcting code that also has a property tester like the kind we were discussing throughout this hour. And then what does that mean? It means that you're looking at a string W, and the property tester should have the following property. If W is in the code, in this linear subspace, the tester should succeed, probability 1. And if it's not, so again, we don't care of one bit flip, we care of W that's far from the code, you need to change many bits, then the tester will succeed with probability bounded away from 1. So there will be a noticeable fraction of rejecting tests. Okay, that's a locally testable code. Now, what are examples of locally testable code? So I'm not going to define these things, but these two examples, the Adamar code and the Irit code, they exactly correspond to the question of linearity testing and to the question of low degree testing. Linearity testing is another way of saying that the Hadamard code has a good property tester. And an open question is to find an error correcting code like these two, but that has good parameters. So in coding theory, we can get codes that the stretch is only a constant. So if you want to send k message bits, all you need to do is send k times 1.1 encoding bits, and you will have good distance. So we're interested in finding codes that also have the good parameters and are locally testable, and that's an open question. But locally testable codes that are even weaker than that, like the two that I mentioned above, are sufficient for constructing PCPs and such objects, and that's why they were studied intensely. So let me tell you what it means to have a locally testable code. Really what it means is that you have a linear subspace, but this linear subspace can be characterized by a stable set of equations. So I'm reaching this stability. Okay, so what is a locally testable code? For this lecture, it's a linear subspace. People can also think about codes that are not linear, but more often than not, codes are linear, so let's focus on that. So the fact that it's a code just means that it's not only a linear subspace, it's a linear subspace where all the vectors have good weight. Don't have a few ones, they have many ones. Okay, so that just means that it's a code with good distance. And we want our code to have low density parity checks. So a parity check, what is it? It's just a vector with very few ones that is orthogonal, or it has inner product 0 with all the vectors in your subspace. Okay, and why is it called parity check? Because to check if a word is in the code word, you look at the corresponding bits in the parity check vector and you apply the parity and you need to check that it's 0. Okay, so there are, it's very easy to construct a code that has low density parity checks, meaning to check if a word is in the code, you need to run through a bunch of vectors that are low density parity check and just do all these parity checks. the set of vectors that is orthogonal, inner product 0, with all these parity checks is equal to your code. Okay, that's very easy to do. If you even select a bunch of random parity checks, you will get a code, a very good code with good distance and so on. So what is the extra sauce that we are missing? We want these parity checks to give us a stable characteristic of the subspace. Okay, so now I'm going to maybe explain this. So let me now move back to the board. Okay, great. So we have something here. Okay, here. So I have something. I don't think we'll get to this part, so I'm going to erase it. So I'm thinking of a code C. It's a linear subspace of 0, 1 to the n. And I'm thinking of I'm sorry, let me remove some more things that are irrelevant. And I'm thinking of these vectors Vi. This vector is a sparse parity check vector. Okay, so let me call it a sparse parity check. Okay, and what is the constraint or the equation that Vi imposes on my code? So the vector x wants to be in my code. You check it against V1, you calculate the inner product, and the inner product needs to be 0. And the nice thing is, because Vi is sparse, maybe Vi is just, for example, Vi can be the vector that's 1, 1, 1, and all the rest are 0. So to calculate this inner product, all you need to do is read the first 3 bits of the string x. So this is like a property testing kind of check, because you're not going to read the entire code word, you only read the first 3 bits. Okay, so imagine that my code is given by a bunch of such parity checks. Maybe V1 is this 1, 1, 1, maybe V2 is 1, 1, 1, some other place, and so on. You have all these parity checks. Okay, so this is your code. It's all the strings that satisfy all of the parity checks. That's fine. Now, what does it mean to be a stable set of equations? So I view these as equations. For example, if the equation x dot v1 is 0, I can think of it as saying x1 plus x2 plus x3 equals 0. And the equation x dot v2 is 0, I can view it as an equation that says, I don't know, x7 plus x8 plus xn equals 0. So what I have in the end is a bunch of equations. And each equation is very sparse. And what I want is to, and by the way, I don't necessarily expect these different VIs to be linearly independent. There could be redundancy. So there could be that there are more equations here than n, and yet the code still has, there's many solutions. So there are many code roots in this space. So when is a system of equations stable? If the measure of how many equations you satisfy can be related to the measure of how close are you to the code. So we have here 2 different measures. One is the probability of rejection, which is, let me spell it out, it's the probability of choosing a random VI of x dot VI not equal 0. So it's the probability of the of one of the equations to be unsatisfied. Or really, it's the fraction of equations that are not satisfied. Okay, so that's one measure. And the second measure is the distance of x from my code C. You see the linear subspace, I have a string. How many bits do I need to change to get into the subspace? Okay, and the system of equations is stable, so the system of equations given by V1, V2, and so on. Remember, I think of Vi as an equation through this for this equivalence, a system of equations is stable if the measures can be related. If whenever one is small, then two is small. Now, by the way, why am I writing it this way? I'm writing only one direction. If one is small, then two is small. So I claim that in this setup, it's always true if two is small, then one is small. Why is this true? Because think of a perfect code word, string x that satisfies every single one of these equations. Okay, now you take x and you flip a bit or 2 bits, okay? What happens, because these VIs, these equations are very sparse, the probability that you flipped a bit that even affected the V1 is very tiny. So when you start from a legal code word and you change just a little bit, you're guaranteed that so the distance number, the measure number 2 is small, you only change a little bit, you're guaranteed that only a few constraints will reject. Really, this is only true if there aren't some bits that all of the constraints touch. But if there is some uniformity, then this part is true.
You needed the matrix is sparse also on the column, right? Not just on the rows, no?
Right. Assuming uniformity and the sparseness in the columns.
Shouldn't this be also related to having not too many redundancies?
Actually, no. So in locally testable code, you have much redundancy. So
no, but you can have the redundancy. The redundancy works against you on a counter example.
Not really, because
the redundancy can change only one without changing two.
Second?
The redundancy can change one without, if I'm adding now dummy vectors that doesn't change. Say that I have n vectors that define C, and now I'm adding another bunch of vectors that doesn't change anything. Right. I'm actually changing one without changing two.
Right, so you're destabilizing my system. I had a good system and you modify it in a way that maybe ruins this, right?
Yeah, so that's my question. Is it, so shouldn't there be in the brackets here, don't you need to assume also something about the redundancy? Or because I'm running one, so it's included inside it.
So my claim was this, that in situations like we discussed, where these the parity checks are sparse and uniform, meaning that x1 occurs in some number of equations, and this number is the same, say, for every index. Okay, so assume this kind of uniformity.
Oh, okay.
Then,
so then
in this direction is immediate, and the more difficult direction is to show that if few vectors reject, the distance is close. Okay, and in fact, it's okay. I'm running out of time, but I want to say it's actually painfully easy to generate such counterexamples. So it's actually very easy to generate examples where all the equations are satisfied except for one, yet the string is very, very far from the code. Okay, and okay, I don't want to go over time. So let me just finish by saying something about PCPs, because I did promise to say something. So the thing is, we have
Irit, our seminar is 75 minutes, including questions.
75 minutes, that gives me 15 more minutes?
Yeah.
Okay, cool. All right. So good. So then I can say a couple of more things. Okay. So what do you want? Do you want me to talk a little bit more about how to get a counterexample, or should I move forward to talk about PCP?
Are we going to talk about how this is related to local property testing, or like as before, you said it's related to linearity testing or something like that?
Okay, let me think about that.
Irit,
So-
it seems that the people vote to hear more about PCP. What is PCP?
Okay, got it. Thanks. Okay, I'll do that. So regarding linearity testing, what does this have to do with linearity testing? So let me just say one thing. Linearity testing is you have a function f and you test if it's linear. So I can define the Hadamard code to be all strings of length 2 to the n. Really, I think of it as a function from 0, 1 to the n to 0, 1, such that the f is a truth table of a linear function. And then the linearity testing that we saw before is really giving us a bunch of these vectors, parity check vectors vi. The vector vxy is just a vector that's zeros almost everywhere, except it has a 1 in location x, a 1 in location y, and a 1 in location x plus y. There's 2 to the n coordinates here. So this is one of the parity check vectors, and the fact that f needs to be inner product 0 with this vector is exactly the check f of x plus f of y equals f of x plus y. So you see that the Hadamard code is a locally testable code. Why are we not happy with it? Because it takes n message bits and encodes them by 2 to the n encoding bits. It's not very efficient. Nevertheless, for PCPs, this encoding was actually used to construct efficient PCPs because you only apply it to small pieces. But let me say something about the PCP, okay? So now I'm moving from locally testable codes to PCPs. So earlier, just now, we defined what it means to be a stable system of equations, but I only talked about linear equations, okay? I don't need to talk about linear equations. I can talk about the equations that are more expressive with that. And for example, the following problem is NP complete. So this means that every problem in NP, every computational problem where you can check the solution efficiently can kind of be reduced or re-expressed as the following problem, which is you have variables x1 up to xn, variables with values 0 and 1. So I think of them as variables over the field f2. And I have equations of the form x1, x2 times 1 minus x3 equals 0. So I have equations with degree, say 3, at most 3, so not only linear. I'm also allowing myself to do equations with degree 3 and at most 3 variables. And what is the problem here? So you get a system of such equations over your variables. And the question is there a solution? So people who are familiar with this thing, this is a very simple way to encode 3-sat, which is a famous NP-complete problem. And okay, so what does it mean that it's NP-complete? It means that you can always search the space over 2 to the n possible assignments and see if one of them satisfies all of the equations. But short of that, there is no polynomial time algorithm that we know to find the solution, even if we know that one exists, and we don't believe that there is such an algorithm. Well, if there is, then P equals NP. Okay, so now I want to understand, is this true? What about when the system of equations is stable? System of equations. So now it should be clear what we mean by stable. It means we again want to relate these two measures. One is the measure of, you have some solution. You want to know what fraction of equations are satisfied by this solution. Okay, the probability of rejection is exactly how many equations are unsatisfied. So that's one measure. And the other measure is how close is this solution to a satisfying solution. Okay, and
yeah, so maybe the word solution, like you have some, I don't know, you said a solution from a solution, right? Like you meant that the first one is not actually a solution. It's just some putting zeros and ones in the variables.
Okay, but the word
Yeah,
solution here
yeah.
is clean, right? Clear, right? It's an assignment of zeros and ones that satisfies all of the equations, right? So I get so what I mean is that given some string x in 0, 1 to the n, I have measure 1, which says just the probability over a random equation in the system of equations. So let me call this system S. So a random equation in S, x satisfies this equation, this probability. This measures how good this string is, how good of a solution it is. And this is one measure. And the second measure is the distance of x to the set of solutions, which might be an empty set. And then we define the distance to be maximal, 1. Okay, where this set is just defined to be all the strings y such that y satisfies all equations. So it's completely analogous to the situation we had before with the code. The set of solutions was our code. The set of equations were the dual constraints, and we measured how many bits you need to change to get to the solution. This is this measure. And we also measured what's the fraction of equations you falsify. So we say that the system of equations is stable if whenever measure 1 is small, 1 small implies that 2 is small. So we only care about this direction, actually. Okay, so we say that the system is stable if this is always true. Okay, okay, so whenever you're satisfying almost all the equations, you're actually, the only reason this can happen is because you're actually close to a perfect solution. Okay, and what does the PCP theorem say? The PCP theorem says every system of equations like the above can be transformed in polynomial time. So even though you don't even know, you don't understand the set of solutions, you're running in polynomial time, can be in polynomial time transformed, translated, I don't know what to say, to a stable one, system of equations. And more things are known. In particular, you can see that if you plug into this theorem a system of equations for your code, you will get a new system of equations. Okay, maybe it will be over new variables, I should say. You're allowed to add variables over new variables such that the new thing is going to be a code and it's going to be a locally testable code. So, but this is a much stronger theorem. It's talking not only about linear subspaces, it's talking also about NP-hard sets, like the set of solutions. Being an NP-hard set means that we don't understand it. We have no way of understanding if it's an empty set or not. Nevertheless, we can transform the defining equations into a stable, or sometimes people say robust, system of equations. Okay, maybe ask me a question so I know. Yeah, I guess I don't have so much time, so ask me what you want to hear.
I mean, I guess that this theorem can be translated now because this specific problem, the 3 satisfy, is kind of every problem can reduce to that, every problem in the NP class. So I guess that it means that there is an analog to every other problem, right? That every NP problem can be translated to a problem
Right.
which is stable. I mean, so it's
every element, every kind of problem in NP can be translated to the system of equations problem, and then through the PCP theorem, it's translated into the stable system of equations problem. So right, so every problem in NP can be recast in a stable way. And what does this mean? One of the reasons people really are interested in this, so I forgot to say, so let me say two sentences. Initially, the way people viewed the PCP theorem is very different from this. It's talking about the fact that if you have an NP problem, It means that someone can write a proof, a witness, which is this solution, and instead of reading the entire solution and checking that it's a good solution, all you need to do is select one of the random equations in this stable system and just read those bits. So this is like a property testing, but of the NP witness. You're asking the NP almighty prover who knows the solution to this system of equation to write down the solution, and you won't even read it. You'll only read a few bits. Which bits? The bits of one of the equations in this stable system of equations. And it allows you to verify a very complicated statement by reading only a few bits. So this is kind of captivating, and also it's useful. People are trying or actually designing now, cloud protocols where you want to check that, some transaction with the bank is actually happening okay. And your iPhone is maybe too weak to do the entire calculation. So what you do is you use a PCP protocol where the checking, it's like a property testing algorithm. It's a very simple algorithm. The phone doesn't need to work hard, but of course, on the side of the cloud, they need to work hard to produce this proof. So that's one kind of interesting application of the PCPs in modern times.
So now when I know that sometimes you say that if there will be a good LTC code, then it will have some implication also for the PCP's theorem. In what sense this will improve the PCP theorem?
Okay, so one more application of PCP, a more theoretical one, is the relation between proving a PCP theorem and studying hardness of optimization problems. So for example, this theorem, the way we wrote it, the fact that a system of equations can be translated to a stable system, it means that not only you cannot find a perfect solution for a set of equations, there is no algorithm that finds even a solution that satisfies 99%, what we call an approximation algorithm. Because if you could always find 99%, then because of the stability, 99% of the stable system implies existence of a solution in the original system. So why am I saying all this? Because if we have a good LTC, it will mean probably, even though it's not enough, it's just probably in the same techniques, you can do the same for the PCP theorem. You can have this transformation from system of equations to a stable one be very efficient. Like in error correcting codes, you only want the amount of overhead to be a constant factor. So if you had n variables initially, now you want only 10n new variables. Currently, we only know PCP theorems with much bigger overhead. And if the overhead will be so short, like 10n, then it will have a lot of complexity theoretic implications I'm not going to go into, but just means much better hardness and approximation results, exponential time hypothesis, all kinds of stuff.
Interesting. Okay. Some more questions? If you have, please speak out because I don't see you all.
Michael, you're muted. I don't know if you're speaking or not.
Okay. If not, then...
Sorry, that was unrelated, Irit.
You wanted to ask something, Michael? No, okay. Okay.
I think I'll take it offline with Irit. I'll send her an email or something.
Okay, Irit, thank you very much. It was excellent, and I think all of us learned a lot. And next week we are going to have Henry Badford will talk. We'll go back to permutation stability, and he will show us the connection between permutation stability and the so-called IRS, invariant random subgroups. So see you all next week.